Adra, that is what we have just Andre helped us to understand. But we want the other ways. Another way. Okay, Josephine. Josephine.
Please, the
Apart from
wavelength in air over the wavelength in any medium.
So wavelength of light in air over wavelength in any medium. Thank you, Josephine. And then what's the last, yes, the last way we can represent absolute refractive index. Equia.
Yeah. The speed of the light in air over the speed of light in
Equia, that's the first thing we spoke about. Okay, so the last thing is using Snell's law, using direction. So sine of or angle, sine of the angle of incidence to the sine of the angle of refraction. And absolute refractive index of a material, written as simply N, nu or mu, is always greater than 1. Adwa, why is it always greater than 1? Why is absolute refractive index always greater than 1, Adwa? Adwa, let's hurry up. Are you there? Adwa, are you there? Josephine.
Yes, please.
Josephine, why is absolute refractive index always greater than 1?
Because the angle of incidence is greater than the angle of refraction.
So Josephine is only using this one to answer my question. But generally, whether it is this, or this one, the numerator is always greater than the denominator. So if you are using this, speed of light in air is greater than speed of light in any medium. And so when you take this ratio, you need to have a value greater than 1. If you use this, yesterday I made you understand that velocity of light, whether in air or medium, is directly proportional to wavelength. So this means that if speed of light in air is greater than speed of light in a medium, then wavelength of light in air will also be greater than wavelength of light in any medium. And for light to travel from air to any material, I will be greater than R. Please, for light to travel from air to any material, why would I be greater than R? Why will I be greater than R? For light to move from air into any other material, why would I be greater than R? Equia, why will I be greater than R?
because the angle of incidence is greater than the angle of
Y.
refraction.
We are Y. Y. What? For light to move from air to any medium, why will I be greater than R? Just thing.
Stage, yeah, because like the density of the air is lesser than the rest of the material, like the other medium.
So
So when it moves from like maybe I to maybe air to maybe water, the R will refract closer to the normal. So
exactly. Ekuyadoma, I is greater than R because whenever light moves from less dense medium into a denser medium, the ray of light will be refracted towards the normal. That is why I will be greater than R. So if this is air, we are talking about absolute, and this is any medium. Because density of the medium greater than density of air, this incident ray, I, at this boundary or junction, the refracted ray will bend towards the normal. And this is R. So I is greater than R because the light is from air to a denser medium. Class, please, is that okay? Demaris, Andre, and Ekuya.
Yes, please.
Andre, are you there? And Ekuya.
Yes, please.
Yes, sir.
Okay, so usually the thing is, I am fond of probing the thing to the basics so that you understand, I mean, the reason why. Is that okay? So this is the reason, meaning that if it is not absolute, refractive index, then the first medium can be denser medium to air. Here, I will be less than R because the refracted ray will bend away from the normal. So I will be less than R, or R will be greater than I. Do you have any question? All right. Then let's continue to look at reverse refractive index. Reversed refractive index. The name is even clear. Reversed refractive index. So when the path of light is moving from before, just now we've had air to water, absolute refractive index of water. Of course, this is the normal. The absolute refractive index is equal to sine I over sine R. So the light is from air to water. Now, when I reverse the path, assuming I is maybe 25, and R is 15. When I reverse the part, air, water, then this time around, the light ray is from water coming out of air. And then, if it's from air to air, I is 25, R is 15. I'm reversing the part so that I have water to air, but maintaining whatever gave me whatever I had as R. So R, this is now I. This is now I. But it is, we are representing this as R because we are just using the same value of R, 15. Then it means this being I must give us 30. No, 25. So if I want to determine the refractive index, this time the refractive index is from water to air. Before, it was air to water. So I have sine of R over sine of I. Now I'm using this. This is the incidence as R because it's the same value I'm using. Angle of incidence 25 gave me an angle of refraction of 15, meaning that if I reverse the path and take angle of incidence to be 15, I must get an angle of refraction of 25. So that is what I'm using here. Please, are we okay?
Yes, please reschedule.
Okay. So this concept is known as the reversed refractive index. This concept is the reversed. This is the reversed refractive index. Meaning that whenever light travels from medium 1 to medium 2, the refractive index for such direction of light is, the light is from medium 1 to medium 2. If you multiply the reverse refractive index, medium 2 to medium 1, this product must give you something. Let's see. So we have refractive index from air to water times the refractive index from water to air. There is the absolute. There is the reverse. This product must be equal to sine I over sine R, air to water, times sine R over sine I. And they will cancel to be equal to 1. So the absolute refractive index of a material times its reverse refractive index, the product must give you 1. Or whenever you have the refractive index of a material and you reverse it, the product of the actual and then the reverse must be equal to 1. Please, are you okay?
Maybe.
Are you okay, class?
Media.
Josephine, are you fine? Andre, are you okay? Adjoa,
Yes, please.
so this is the whole concept of reversed refractive index. Okay, so the product of the original by the reverse refractive index must be equal to 1 or whenever you have the absolute must be equal to 1 over the reversed. Okay, so generally all that we are saying is this. Generally all that we are saying is if you have two media and you take the refractive index from 1 to 2, when you reverse it and then the refractive index of the reverse, the product of the original and then the reverse, this must always be equal to 1. So it's all about two media. If the media xy, refractive index of xy times refractive index of yx, this product must be equal to 1. Meaning there's the original and we are reversing it. That's it. All right. Then let's try to understand relative refractive index. Relative refractive index. Andrea, are you asleep?
No, please.
Okay. You can't sleep, you lie. What is relative refractive index? With relative refractive index, it's about whenever you have any two joint media, which technically we'll call as composite media. So composite media refers to any two joint media. The point is we can't join air to water. We can't join air to glass. Okay, so here we are looking at optical material that can be joined. So for relative refractive index, we are not, though we can compare. Relative means a state of comparison, okay? Though we can compare the refractive index of air to water. But for relative refractive index, we are more or less looking at comparing those ones we can compare, join and compare. Is somebody with me?
Yes, please.
So we are looking at those we can join and compare. But that does not rule out those ones we can't join because we are looking at the two media acting at a common boundary. So, assuming you have two materials joined, and there's a boundary between the materials. So, material A with density A, and then material B also with density. Okay, instead of density, let me express it in absolute refractive index. So the actual refractive index of A is mu A. Then refractive index of B, mu B. This is the boundary between them. There's the boundary and there's the normal. The normal is always perpendicular to the surface. And this normal in ray diagram or under light is always there because that is where we measure angle of incidence and angle of refraction. So, Adwa, if the refractive index of A is greater than refractive index of B, what will happen? Adwa, Asante, Otulia. If light is moving through medium A and the refractive index of A is greater than refractive index of B, what do you think will happen? Dear Adwa, dear Adwa Otulia.
This is the real and away from the normal.
Adwa, is
Towards the
that
normal.
the ray will bend?
Towards the normal.
Why? Bename why dear unim? Why? Why would the ray bend towards the normal? If, let me bring the drawing up here. So mu of A, mu of B. So mu of A is greater than mu of B. So if you have this situation, Adwa, are you still standing by your word that the ray bends towards the normal or you are changing it?
No, I'm not changing.
So why? Why would the ray bend towards the normal if mu of A is greater than mu of B? Equiadoma. Equiadoma. It's Equiagon. Oh, Equia, can't you hear me? I hear you. Equia. Hello. Okay, Josephine,
Yes, please.
do you have an idea if mu of A is greater than B? Do you have an idea of what will happen?
Mr. Edia, please, I think it will bend away from the normal.
Why?
I think that we said that the refractive index is the ability of a material to deviate light. So if the refractive index from A is greater, that means that like when it's the ability for the light to pass through that material A will be difficult, like to be high. So it will be close to the normal. So when it gets to medium B, which has a less refractive index, that means to bend away from the normal.
Josephine, thank you so much. Akuya, Adwa, thank you so much. You see, the point is that a material with a greater refractive index also has greater density. So it also implies that the density of A is larger. So absolute refractive index connects to density. If I can deviate light better, then it means I'm denser than you are. The refractive index of glass, 1.5. Refractive index of water, 1.33. What it means is that, and we all know glass is denser than water, right? So a material with a larger refractive index also has a larger density. So if light is moving from a material with a greater refractive index, it means its density is also greater than the second. So if this is denser than this, then the light will slow down in this and speed up in this. So over here, it will deviate away from the normal. If it's on the other way around, Demaris, are you following?
Yes, please, you said yeah.
It's from the other way around. That's rho of A, rho of B, or mu of A, and then mu of B. And mu of A is less than mu of B. Then it means, what it means is that this is less dense and this is denser. So when the light is incidented here, this time around, because B is denser than A, it has to deviate towards the normal. So that is the meaning of these things. Okay. So if you have any two composite media with the absolute refractive index of those media, mu A and mu B, and here we are looking at this greater than this, then the light refracted ray bends away from the normal. So for any two composite media, the product of the absolute refractive index, let me write it in statement form before we look at equation. For any two joint or composite media, the product of its absolute refractive index and the sine of the angle of incidence in the first medium must be equal to, let me connect the equal to sign here, must be equal to the product of the absolute refractive index of the second medium and the sine absolute refractive. Must be equal to the product of the absolute refractive index of the second medium and the sine of the angle of incidence, refraction. Second medium. And mathematically, this is what we are saying. Mu of A, that is the absolute refractive index of medium A, times the sine of the angle of incidence in A, I. I'm referring to this I, must be equal to mu of B times the sine of angle of refraction in medium B. And this equation stands as it is because, you see, when you have any two joined media and light is incidented, when you multiply the absolute refractive index of the first medium by the sine of the angle of incidence in it, this will give you a certain constant value number. Now, when you pick the absolute refractive index of the second one and multiply by the sine of the angle of refraction produced by I, don't forget, I will produce a corresponding R. So whatever I produces is the angle of refraction. When you multiply the absolute refractive index of the second medium by the angle of refraction produced by the angle of incidence, this is also equal to a constant value K. Numerically, this can be maybe any number 2, 1, 2, and this will also be the same number 1, 2. The reason for which, if this is equal to K and this is equal to the same value K, then we can equate this one to this one. This is how we came by the formula or this relation. Please, are you okay?
Yes, please.
Okay, so with this, let's find sine from this equation. Let's make sine I over sine R the subjects. Demaris, help me make from this equation, make sine I over sine R the subject.
Mr. Area, please, I'm coming. Mr. Area, we should make a sin I on sine R.
Pardon?
Please, the subject should be sine I on sine R.
And that's what I've done.
Mr. Area, please, I don't get you.
From this equation, make sine I over sine R the subject. From this.
Okay.
Okay, let's Josephine, quickly do that for the marks. From
Mr. Area,
the
please.
Mhm.
You multiply through by UA
No,
times sine R.
no, Josephine, give me the final results.
Sine I over sine R is equal to UB over UA.
I am mu mu
Mu, mu,
mu
B,
b over,
mu A.
yes, that's how it's supposed to be. Now what is sine I over sine R?
Mr. Area, the W, the
What is sine I over sine R?
Mr. Area, N.
That is n. Good. This is absolute refractive index of, we can't say absolute refractive index, but because light is moving from A to B, it means the refractive index of light from A to B is equal to mu of B, the ratio of their absolute refractive index, mu of B over mu of A. And this is what we call as relative refractive index. This is relative refractive index of a material. So we have two composite joined materials, AB, and we are comparing their refractive indices. So the refractive index of A with the refractive index of the material B with respect to A is equal to the absolute refractive index of B over the absolute refractive index of A. Let me explain this one too. So when light is moving from A to B, material A to material B, the light is from A, enters into B. If the If B is denser than A, light deviate towards the normal. Okay. Because this direction of light gives me refractive index of the second medium. And what's the second medium? B through A. So the first letter represents where the light is coming from. And the second letter represents where the light is entering. So we term this as refractive index of the second medium, B, with respect to A. That with respect to A is that through A, or we are comparing refractive index of B through by looking at the refractive index of A. All right. So this is, if I write it this way, it actually refers to refractive index of B with respect to A or through A. If it changes to be B A, if the medium changes to be B A, then it simply means this time we are looking at the refractive index of the second medium A, but through B. So this is equal to refractive index of material B A with respect to B. So absolute refractive index from air to maybe water refers to refractive index of water with respect to air. Please, are you okay with the representation? Are you okay?
Mr. J, please, the ANW one, the last one.
I'm coming in. Please be here, class. This is, you see, this is absolute refractive index of water. The first medium is air. The second medium is water. What this means is that, yes, this is absolute refractive index because the first medium is air. But what it also means is that this, we can also refer to this as refractive index of the second medium, water, with respect to the first medium, which is air. Okay, which can be written as just N or mu. When you see just this or this sign, it means absolute situation. Or I can also write mu or nu of W. This is also absolute. Demaris, are you okay?
Yes, please, Mr. J, thank you.
All right. So this is the meaning of relative refractive index. So whenever you have two composite material, 1 and 2, with refractive index mu and mu of 2, when light travel from medium 1 to medium 2, whether burning away or towards. The products of the refractive index of the first medium and the sign of the angle of incidence in it must be equal to the refractive index of the second medium and then the sign of the angle of. So sine I over sine R is equal to mu2 over mu1. And this is refractive index of relative refractive index of medium 2 with respect to 1, which is mu2 over mu1. This expression is relative refractive index. All right. And we've also learned that for any two composite media, if you take the refractive index of 2 through 1 and you reverse it, the reverse refractive index, this must be equal to what? This must be equal to
Mr.
this
Dia,
one.
1.
1.
Okay.
So we've done reverse refractive index and relative refractive index. Okay, so Adwa, are you there?
Yes.
We have 2 to 1. Help me to determine the relative refractive index from 2 to 1. Help me to determine the relative refractive index from medium 2 to medium 1. Adwa, are you there?
Yeah. Is the relative refractive index of 2 be greater than 1?
No, I'm saying help me to determine the relative refractive index, the expression for the relative refractive index. Similar to what we did here. That's what I'm saying.
Yes. It will be the mu1 over mu2.
Mu1. So please, the order is that, look, when we have 1, 2, it is equal to mu2 over mu1. So if I'm giving you 2 from 2 to 1, then it must be mu1 over mu2. The absolute refractive index of medium 1 over the absolute refractive index of medium 2. That is how to picture it. Simple. All right. Now, when you have 3 composite media, 3, this time we are joining 3 materials, or looking as if we have 3 materials joining. We have medium 1, we have also this as medium 2. 1, 2, 3. Please, the boundary separates the two media. So once this is a boundary, this is the first medium. The second medium starts from here and ends here. That's why this is medium 3. So mu of 1, mu of 2, mu of 3. And we are looking at a certain order. The order is that refractive index of 1 must be less than refractive index of 2, must also be less than refractive index of 3. It doesn't mix up like that or the other way around. That's refractive index of 3 greater than refractive index of 2, also greater than refractive index of 1. This rule works on this order. It shouldn't just be mixed for you to just apply. No, it must fall within this order, either increasing refractive index or decreasing refractive index. Deviation of light occurs at the boundary. So this is a normal. So when you incident light here in the first medium, mu of 1 is less than mu of 2. So when the light gets to this boundary, will it deviate away or towards the normal? Andre, are you there? Oh, Andre is gone. Hello, Andre. Okay, she's gone. So, Adwa,
Yes, please.
if mu of 1 is less than mu of 2, when the light gets to the boundary, will it deviate towards or away from the normal?
You will deviate towards.
Good. So, then the refracted ray also gets to this boundary. Also gets to this boundary. When the light gets to this junction, will it deviate towards or away? Mu 2 is less than mu 3. Adwa, what will happen?
It will also deviate towards.
So boundary 1, boundary 2. So it will further more deviate towards the normal. Then we see the ray finally coming out through air and will now deviate away. Okay, please, we are not using 4 different media. It's like we can take this to be air, water, glass, and this is air, the same air. So it is entering into air and coming out of air. All right. This is the angle of incidence. This is the angle of refraction 1, R1. This is another angle of refraction, R2. And then when the light starts from A, comes out from A, in fact, refraction along parallel plane. So refraction of light along parallel plane has said that the angle of incidence equals angle of immersion or emergence. And this is, the light is emerging out of these three media. So this angle becomes the angle of emergence E. Because these planes, boundaries are parallel, you are saying that refraction along refraction of light along parallel plane, angle of incidence equals the angle of emergence, meaning I would be equal to E. I will be equal to E because these are parallel plane. So refraction of light along a parallel plane, angle of incidence equals the angle of refraction. The reason for which this angle must be equal to this angle. Please, are we okay?
Yes, please, yeah.
All right, so let's look at deviation of light at each boundary 1, 2, 3. So we have boundary 1, boundary 2, and boundary 3. If you take boundary 1, Snell's law, refractive index from medium 1 to medium 2 is equal to sine I over sine R, R1. Because this is I, this is R1. Help me determine refractive index from medium 2 to 3. Yes. What's the refractive index from medium 2 to 3? Anybody? Refractive index from medium 2 to 3. What do I write? In terms
Mr.
of,
Jeb, will it be
yes, just give it a try. Applying Snell's law. Now, what is this angle? What is this angle?
please? We can't see the angle.
Medium 1. The light deviates towards the normal. Then this is 1, 2. Then we have medium 3 is here because 3 is denser than this one. There's further deviation towards the normal. This we are referring to as I. This is R1. This is R2. So my question is this. If this angle is R1, what will be this angle? So this angle in question is the same as this one. So if this is R1, what will be this angle?
R.
R1 because of what rule?
Alternate angles.
Alternate angles. And don't forget, when light travels through the same medium, its path is never bent. So so long as the light travels through within the same medium too, this angle would also be equal to this angle because it's the same medium, no deviation of light. So Demaris, what will be refractive index from medium 2 to 3? What will be the refractive index from medium 2 to 3? Yes. In terms of Snell's law.
Please, in terms of
Snell's law. Okay. Anybody
Mr.
to contribute?
Sine R1 over sine R2.
So we are looking at refraction here. So sine, the angle of incidence, which is the same as this one. This angle of refraction is the same as angle of incidence here. So if this is R1, this is also R1. And we have indicated this to be R2. So this also becomes sine R1 over sine R2. Demaris, is that okay?
Yes, please, Mr. Yeah.
Then let's look at refraction of light at boundary 3. That is, this is 3, from 3 to 1, because this is the same as the first medium, air. So refractive index from 3 to 1.
Mr. Adrian,
Hello.
please I have a question.
Ask.
Please, but right now we found the refractive index from 3 to 2. Like from the one we just found.
2
The
to
refractive
3.
index
2 to
from
3.
2 to 3. So,
Yes.
but with this one we use like the angle of incidence here is equal to the angle of refraction.
Yes.
But we are doing 2 to 3. That means like it went into the third medium.
Josephine, we are looking at the light ray coming from medium 2 and deviating at this boundary and entering medium 3. So deviation of light occurs at the boundaries. And so we looked at refraction of light from 1 to 2, which is sine I over sine R1, which is this one. Then we look at the deviation which would occur here from 2 to 3, sine R1 over sine R2, which is this one, which is this marked one. We are now looking at the light is moving from medium 3 and coming through air. So deviation at this boundary. Okay. Refraction of light from 3 to 1. That is the next thing to look at. Are you okay?
No, Mr. Ejia.
Mm-hmm.
If I'm saying that, so like, have you seen in the second medium, the arrow, the light ray, that's the
Yeah.
incident ray, right?
Mm-hmm.
And the second and the third medium, the
Mm-hmm.
arrow there, where we've written R2, that's the
Yes.
refracted ray.
This is the refracted ray. The arrow is also here.
So
Look at,
Mr. Ejia,
we can use this same diagram. This is 3. So use this one. This is medium 2, medium 2, medium 3. Mm-hmm. Ask your question.
so like, if the from the mid when we did the alternate angle, the R1 will be same as the first one, the incidence with the angle, so we get R1. But
Yes.
the R2, isn't it like vertically opposite to the R1?
No. You see, medium 2 is less in density than medium 3. Or medium 3 is denser than 2. So when the light gets into medium 3, it will further be deviated. So this would be smaller than this R1.
Yes, please.
Okay. Because medium 3 is denser than 2, when the light enters, get to the boundary, it will further be deviated. So it will not look like if this is what you are saying. If it's moving like this, then you can say this angle would be equal to this angle by vertically opposite rule. Okay. Josephine, are you okay?
Yes, please.
The ray would further be deviated towards the normal because 3 is denser than 2. So R2 will be different from R1. Small line. Are you okay?
Yes, please.
All right. So how do we express the refractive index at the boundary 3? How do we express the refractive index at the boundary 3 as light moves from the third medium into air? Yes, Josephine. Refraction at this boundary.
So it will be sine R2,
Sine R2
all over sine E.
or sine E. Thank you. So it means that whenever you have 3 boundaries, Andrea, are you there? Or she's gone forever?
I'm here.
Whenever you have 3 boundaries, and the boundaries are in that order of increasing or decreasing refractive indices. When you have mu1 less than mu2 less than mu3, the product of their refractive indices, mu1 to 2, this one, times mu2 to 3, 2 to 3, and mu3 to 1. You have So mu 1 to 2, from the first medium to the second medium, from the second medium to the third medium, and from the third medium back to the first medium, you have, this will be equal to sine I over sine R1 times sine R1 over sine R2 times the last one, sine R2 over sine E. This and this will cancel out. So sine R1 will cancel out. This and this would also cancel out. And you have sine I over sine E. But I earlier told you that for refraction of light along parallel plane, angle of incidence equals angle of emergence. So it means that I equals E. And so this and this will also cancel out. Meaning, if you have any composite three media, okay, and it is such that it is in increasing order of refractive indices or decreasing order of refractive indices, the refractive index, product of the refractive index at the boundary is equal to 1. So mu1 from 1 to 2 times from 2 to 3 times 3 to 1 must be equal to 1. If you have four media, it will be the same thing. 5. So 2, don't forget, we've done it for 2. We are doing it for 3. We'll end at 3 and then apply. So if you recall, for any 2 media, the refractive for any 2, the refractive index from 1 to 2, and the reverse, mu from 2 to 1 is equal to 1. For any 3, 1 to 2 by 2 to 3 by 3 to 1 must be equal to 1. 4, it will be on and on and on. So if you have maybe air, water, glass, I said it should be either an increasing order of refractive index or density or decreasing order. That is why I'm starting from air, the denser one, and the most dense media. So it means that the refractive index from air to water times the refractive index from water to glass times the refractive index from glass back to air. This product must be equal to 1. A very important rule which we'll be applying in our optics life. Please, if you have any question, ask. Let me get a question so we can quickly apply. Okay, I want you to put this question down. Are you ready? Are you ready?
Yes.
So the refractive index the refractive index of glass with respect to water.
Yeah, please can you come up? Come on.
The refractive index of glass with respect to water is 9/8. The refractive index of glass with respect to water is 9/8. Then the refractive index of glass with respect to air is 3/2. The refractive index of glass with respect to air is 3/2. Find the refractive index of water with respect to air. Find the refractive index of water with respect to air. Okay, so 3 minutes.
Mr. Dia, please can you repeat the question again?
The refractive index of glass with respect to water is 9/8. Glass with respect to water is 9/8. The refractive index of glass with respect to air is 3/2. Find the refractive index of water with respect to air. Find the refractive index of water with respect to air. So 5 minutes. Try it. Let's see what you can produce. Minute is due. Your 5 minutes is due. Are you true? Hello, are you true?
Yes, please.
The rest of you. Andre, are you true?
No, please.
Equia,
No, please.
Josephine,
Yes, please.
Josephine, what did you get?
Miss, I had 16/27.
Demaris, have you finished?
Yes, please. Mr. Dia, please. I got 4 and 3.
Equia, are you close?
Studio, please, I had 0.59.
Express it in fraction.
16 on
I think,
27.
I think it's wrong. The question says, Find the refractive index of water with respect to air. So meaning you have to look for absolute refractive index of water. Andre, are you close? Andre, are you close? Out of the answers, I think Dimare's answer is the right answer. The answer is 4 on 3. 4 on 3. Let's go through it. So we are told that the refractive index of glass with respect to water is 9/8. So refractive index of glass with respect to water. So water to glass, 9/8. Then refractive index of glass with respect to air. Air to glass. 3/2. Find the refractive index of water with respect to air. Water with respect to air. Now, we have air, water, glass. So, refractive index of air must be less than refractive index of water, less than refractive index of glass. So, it follows the order. If this is the order, then we can say that refractive index of water with respect to air times refractive index of water with respect to glass times refractive index of glass with respect to air must be equal to 1. Air to water, water to glass, glass back to air must be this. Are we okay here?
Yes, please.
Now, this is what we are looking for. Do we have this? Water to glass, yes. 9/8. Do we have air to glass?
Yes, please.
Do we have glass to air? What we have here is air to glass, not glass to air. But there's one thing that we know, and that is the refractive index from air to glass, and then the product of its reverse, glass to air, is equal to 1. So we have to look for this, but we have this. Therefore, we make glass to air the subject. And this is equal to 1 over air to glass. So we have 1 over 3 on 2, which is 2 on 3. Are we okay? Josephine, Epia, are you okay here?
Yes, please.
Okay, so if this is it, you have this, can't you find that you have this one? Water to glass is 9/8. You found glass to air, 2 on 3. Determine refractive index from air to water. This becomes times, you have times 9/8 times 2 on 3 This is equal to 1. So this is 3. This is 4. Therefore, refractive index from air to water will be equal to, when you make this a subject, it will cross multiply 4 on 3. And because this is absolute value, air to water, this will be greater than 1. Please, is that okay?
Yes.
So it isn't, when you understand the principle, it's not a difficult question at all.
Mr. Adrian, please a question.
Okay.
Please, after I got a 3 on 4, please, what did you say will happen before it becomes 4 and 3 as the final answer?
You see, we have refractive index from air to water. When we cancel, we have times 3 on 4 is equal to 1. And you are looking for this one. What will you do? Either you multiply through by 4 on 3 to cancel, or you cross multiply. So if I have to multiply through, I have this 3 on 4 times 4 on 3 at both sides. And this will cancel. So I have refractive index from giving us 4 on 3. Are you okay?
Please,
Mr.
thank
Adrian.
Hello. Is
Mr.
everybody
Adrian,
all
please, I have a question.
right?
Mr. Adrian, the question didn't state that it's moved from maybe air to water, then to glass. So how will you know and use that concept to solve?
Okay, when I was teaching this, I initially told you that this concept doesn't work on anyhow. It works on increasing refractive indices or decreasing refractive indices. So when the question is given to you, you must apply that this product blah 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 is equal to 1 when we have 2, when we have 3, when we have 4. It wouldn't work when it is mixed. So you would have to arrange it that either in increasing refractive indices, air to water, water to glass, or decreasing refractive indices. I said that before we even derived the relation. Are you okay?
Yes, please. Thank you.
So when it is mixed, it doesn't work. It would work when you have an increasing refractive indices of the media.
Mr. Dear,
Hello.
the question, they didn't tell you whether it's increasing or decreasing. It was like mixed.
At some yeah, you haven't understood it. They didn't tell us, but it works. The concept works on when you have increasing. So you would have to arrange it as such to apply. The refractive index of glass with respect to water is 9 on 8. So they've given you the refractive index of water to glass. Then that of glass with respect to air is 3 on 2. So they've given you this. But you know that the principle works on increasing when you are light is moving up, increasing refractive indices. So you would have to arrange it as such and work with it, even though it appears mixed. Is that okay?
Yes, please.
Okay. All right. So I'll send another question so you work or try and then send it to me for marking. Okay. I'll drop it in the group. Adwa, are you okay? You left. Andrew too left. Okay, so bye-bye. You have the question.
Wow.